Well, I think the folks who are going to show up are here, so this is excellent. My name's Parker Glynn-Adey. I'm one of the co-organizers of the seminar. Today I'm going to talk about the probabilistic method. We're going to do one example, sort of a foundational example of the probabilistic method. As I speak, if anything comes up that you want more details on, please throw a question in the chat. I'm happy to slow down, talk about things. I want you to get as much out of this seminar as you can. I want this to be a place to chat about math instead of just a lecture. So let's get started. Let's jump in and check out the probabilistic method. Okay, so what we're going to talk about is some mathematics pioneered by a Hungarian mathematician, Paul Erdős. He absolutely revolutionized the field of combinatorics by introducing the probabilistic method and has the most publications of any mathematician ever. So extremely prolific, the legend himself, as Ben Chislett says. If you haven't read it, there's a book, The Man Who Loved Infinity. Great bio of Erdős, because he was quite the character, had a very interesting life. But what he introduced was this way of thinking about combinatorics, where we think about things probabilistically, and it absolutely revolutionized the field. So just to get us started, which of these sequences do we think is random? Just throw an answer in the chat. Have a look at them. Which one do you think is more random? Yeah, we're getting some votes for one. The first one, yeah, for sure. The second is not random. Right, and that's sort of like if I told you that I took this coin and I flipped it and I got heads, tails, heads, tails, heads, tails 32 times in a row, you'd be somewhat surprised. You'd think I'm pulling your leg or something. That would be very unlikely. But the popular opinion is correct. The first one I got by flipping a coin. It was randomly generated. Now, one thing I want to illustrate with these examples is that predictable patterns tend to look non-random. And in mathematics, we often have some kind of construction, some kind of formula. This is a constructive formula that gives us this sequence. Right? So this is a constructive or algebraic or kind of formula for something, yeah, for the sequence of head and tails. And when we're working in mathematics, some of our conjectures might involve things that don't have nice constructive or algebraic formulas associated with them. And what Erdős realized is that by looking at random examples, we can get at some of those mathematical examples that we couldn't get at as constructively. And it's a very, very powerful move, moving away from these formulas. So we're going to use a tool from probability in this talk just to get a sense of where people are at. Could people say in the chat what exposure they've had to probability before, if they've seen it in a class? Yeah, Ben, it's a really, really deep insight. We're going to see how this plays out in combinatorics. But if anyone's taken a course on combinatorics or if anyone's taken a course on probability, could you just throw that in the chat? Okay, we have one person with stats, B52, B57, measure theory a long time ago. Yeah. Learned random variables like last week. Okay, so there's a couple people who haven't had much exposure to probability. The stats B52 people, you're fine. You're going to B57, B52. Those are a great prep for this material today. For people who haven't seen it, what we're going to really use about probability is that a probability is a number between 0 and 1. Okay, so we're just going to use the fact that this is going to be bounded. And it's customary to write omega for the space of all events. Okay, so this is all possible outcomes of some kind of an experiment. And a random variable is neither random nor a variable. It's a function. So it's a function that looks at all of our possible events and assigns a real number to them. Okay, so we define this thing called the expectation, which is where we take the outputs of a random variable and multiply them by the probabilities of the random variable taking on that value. Kind of an insight is that this is kind of like a integral. This is kind of like the integral according to probability. Okay, so what we're saying is, what is the expected output of this random variable over all possible inputs? So I want to give a nice simple example of this. So your co-organizers are going to toss a coin. If the coin comes up heads, then I have to give Lisa Jeffrey $500. And if it comes up tails, then she has to give me $100. Lisa, do you want to play this game? Oh,
I don't want to cheat you. So
come again?
It's very much in my interest, but at least if the coin is fair, then
yeah.
But
yeah, so,
I don't want to cheat you.
Oh, I see. So you're going to be honest. This is good. So
yeah.
So right. So immediately we see somehow this is unfair to me. So what is our event space here? Well, our event space is, does the coin land tails? Does it land heads? And then our random variable, and we'll write this from Lisa's perspective, is that if this comes up tails, then you lose $100, and if it comes up heads, then you gain $500. Okay, so we're taking events and we're assigning them real numbers, and then the expectation of this thing is a half the probability of coming up tails plus a half times the value for heads, and we get a number, $200. So what this is saying is that if we played this game a lot, and I don't want to play this game at all, but if we played it many, many times, on average, Lisa would win $200 a toss. Right, so because this is positive, this is good for Lisa. Does that, so someone said they just learned, Husu Shen Li, you just learned random variables last week. Does this work with your understanding of random variables? Is this okay? Yeah, right, cool. So sort of the expected output of this coin toss is that Lisa gets $200 on average. Excellent. Okay, expectation can help us calculate interesting things about large events. So suppose that we toss a coin 100 times, right? So we sit there all day tossing this coin, and we ask ourselves, how many heads should appear if we toss the coin 100 times? Okay, so we're going to let X be the total number of heads. Now we'll calculate out our expectation. Right, so we're going to add up. Oh, actually, this sum should go from 0. Right, it's possible that no heads come up. So we multiply the number of heads that we see times the probability of there being that many heads. So we get this kind of formula where we have, these are all of the times the coin comes up tails. These are all of the times it comes up heads. Those group together to give us 1 over 2 to the 100. And now we have to evaluate the sum. And I actually don't know how to do that. But that would be the expectation. So when we're doing these calculations with probability, we can sometimes get formulas where we're like, this is kind of complicated. But, you know, we could maybe ask a calculator or something what this is. And this is like the kind of like thing that you might see on like a contest math kind of problem solving thing. But I want to look at this another way. We're going to use a tool regarding expected values, which is called linearity of expectation. So expectation is like an integral, where we integrate over our probability space. So it should be kind of a linear thing. What that means formally is that if we have 2 random variables, x and y, then we can split up the expectation of their sum in this nice linear way. Okay, and this is going to give us, oh, just before we move on, are people okay with this use of the word linear? Yeah? Okay, yeah. Nice, so far so good. Yeah, you know, we've got sort of alpha x, beta y, and we split that up somehow. So it's linear. Nice. And what this is going to do is it's going to give us a tool that breaks up these really complicated events into really nice, simple events that we can measure the probabilities of easily. So let's try that example again. We're going to toss our coin 100 times. How many times should heads appear? We're going to let x be the total number of heads. And notice that that number of heads is actually just a sum of, is the first coin ahead, is the second coin ahead, is the 100th coin ahead, right? So what these random variables do now is they say, okay, this is going to be 1 if the kth coin toss is heads, and it's going to be 0 if the kth coin toss is tails. And now this is like a really easy to understand event, right? Now it's just 50-50 with 1 coin. So linearity of expectations says we can take x, write it as a sum of each of those expectations. Each of those expectations is really just a single coin toss. So it's going to be a half. Lovely. And this makes sense. On average, we sort of expect half the coins will come up heads. So if you're into this kind of problem solving stuff, this might be a nice move to say that this is actually also equal to right? That's like a really nice, fancy way of evaluating that sum, is to realize, oh, I could break this up as an expectation. Fancy move, but linearity has saved the day for us. So there's our sort of our crash course on expectation and linearity of expectation. I'm now going to get into sort of the heart of the probabilistic method. Okay, the kind of the main idea and what this lets us do in combinatorics. So if we have a random variable that always outputs a non-negative number, and if we expect that that is less than 1, then it has to be 0 somewhere. So we might not be able to find where x is equal to 0. The combinatorial objects we're looking at might be really super complicated. We might not be able to find one, but if we can prove that an expectation is less than 1, then somewhere there has to be a 0. Earlier on, I said, we like constructive methods. We might not be able to get a constructive method to find when x is equal to 0, but randomly, if the expectation is less than 1, then somewhere out there has to be a place where x is 0. Okay, I'm now going to demo this with a slightly silly example, but I think it's illustrative of the big idea. So there exists a series of 100 coin tosses without 99 consecutive heads or tails. And like I can hear sort of in the Zoom universe, I can hear people groaning. Of course, there's a series of 100 coin tosses without 99 consecutive heads or tails, but I want to give a non-constructive proof. Okay, the probabilistic method often gives us proofs of existence, but it doesn't actually give us the thing. So what we're going to do is we're going to let x be the number of occurrences of 99 heads or 99 tails. Linearity of expectation lets us say that we can write this as a sum of 2 events. If we have 100 coins, which I'm going to draw as a very small number of coins, either the first 99 coins have that property, or the last 99 coins have that property. Okay, so we can say x0 is this event where the first coins have that property, and x1 is where the last coins have that property. Are we okay with why there are just 2 events, what these events mean, what these random variables mean? Yeah, River's got it, Kevin's got it. Yeah, if we were asking for like 10 consecutive heads, then we'd have 90 events or 91 events. But because we're asking for 99, it's either the first 99 or the last 99. Okay, so we'll define these 2 random variables. And now we can calculate the expectation using linearity, which is going to be the sum of these. Okay, so what's going on here? We've got that there's 2 ways this could happen, right? This could either be all heads or all tails. And then we need 99 coins to land a particular way. So this is our term corresponding to x0. And then again, we've got this guy could be heads or tails. 99 coins need to land a particular way. And there's our x1. Okay, so notice I don't need to know much about these events. I just need to know how many of them happen. I add them up and I get 1 over 2 to the 97. Very, very, very low expectation, right? Very much smaller than 1. Right, so we've got that this thing's much smaller than 1. So lo and behold, there is some event where x is 0. What a shock. Oh my gosh. But this proof is interesting. We don't actually have to construct an example. If we wanted to construct an example, we could do something very simple. One of the cool things about the probabilistic method is that if the probabilities are so small like this, then almost any example will work. I have a very, very short computer program here on my other screen. And what this computer program does is it tosses a coin 100 times. I don't even need to toss it. And when I do that, when I toss the coin 100 times, lo and behold, there's an example of the object I'm looking for. Right? Almost all coin tosses have this property. Okay, so I didn't need to go and construct one. I knew that one existed, and my construction is that almost all of them have this property. Okay, so there's sort of the silly, can the same apply? Yeah, can the same idea be applied to 97, 98? Yep, totally. Kevin's got this cool idea. So what about h to the 98? Right? Yeah. Yeah, we could totally do that. And right, yeah. So Ben, that's also an awesome question. I'm going to finish up with Kevin's first. So what would we get? I guess we'd get x is x0, x1, x2. And then we would then we do the same kind of thing, and we get like, I don't know, maybe 8, maybe 6 over to the 98, which would be less than 1. So a cool question kind of coming from Kevin's question is, when does this strategy stop working? Right? What's the cutoff? Yeah. So yeah, this would also work for 98 heads in a row. Yeah, and it would this would not work for one head, but yeah, that's a cool cutoff question. And then Ben says, if we can almost always find a constructive example, why do we want a non-constructive proof? Right, so this comes back to that point about like having formulas for things or having like algebra associated with something. So we're gonna see an example where, so that the next example of the probabilistic method where it's hard to construct examples, it's hard to give formulas for examples, and kind of tossing the coin is the best thing that we can do. Yeah, so if we can always find a constructive example. So I would say, to your comment, if we can always find a random example, why do we want a non-constructive proof? Right, and the answer to that is, we want proofs of things, right? We're mathematicians, we want to prove that things exist. So even though an argument like this feels a little bit silly, it gives us a proof of something. Okay, so let's see the kind of the grown-up example of the probabilistic method. Okay, so to do that, we're going to need to define some combinatorics. So the KK Ramsey number is the least n such that any edge coloring, oh yeah, and I should say what this is. This is a complete graph. By 2 colors contains a monochromatic thing. Okay, so this is a lot. This is like a complicatedly quantified statement. Yeah, River, solid question. Has anybody heard of these things before? Just throw a yes or no in the chat. Okay, Jesse's got it. Kevin, River, no. Okay, so like some people have heard of this, some people haven't heard of this. I think it's worthwhile spending some time. Oh yeah, sorry, yeah. Yeah, some people also call this K sub n. Okay, let's spend some time looking at a particular example. I think that this will become a lot clearer if we do a particular example. So on the one hand, I want to convince you that this has to be bigger than 5. And on the other hand, I want to convince you that this is going to be equal to 6. Okay, so we're going to do a super duper fast intro to complete graphs and coloring and all kinds of nice combinatorics. Okay, so the complete graph on n vertices has n vertices and all possible edges. Okay, so it's going to have every possible connection that we could possibly have among these 5 vertices. And what we're going to do is we're going to color the edges of this graph. Okay, so I've colored some of them blue. Now I've colored some of them red. Okay, so now I've cast the magical spell of Ramsey theory. I have colored all of the edges. And notice this coloring has no monochromatic triangles. Right, so if I look at any triangle here, I see like 2 blue edges and a red edge. Or I see 2 red edges and a blue edge. Okay, so what this means is that C5 has colorings without C3s. Okay, so 5 cannot possibly be the third Ramsey number because this is a coloring with no monochrome triangles. So far, so good. Is that all right? Okay, now I'm going to give you the argument that this has to be equal to 6. And this is the kind of thing I remember like reading in some book for dorks when I was in high school. And I was like, this is the real math. Like, this is like a super duper beautiful math argument. And every time I get to teach this to, I just love it. It's like one of my favorite arguments in all of math. So let's check it out. Let's argue that this has to be equal to 6. So what do we do here? Well, we want to argue that any coloring, any possible coloring, has a monochromatic triangle. So let's look at just one vertex. This vertex is going to get connected to 5 other things. Right? It has 5 neighbors. Now, we have 5 neighbors and 2 colors. So any way we split those neighbors, right? Any way that we like group them together, 3 of them are going to wind up being the same color. So let's assume these 3 have to be red. Okay, so just a little note there. Okay, so by the pigeonhole principle, we have to get 3 red. I mean, it could be 3 blue, but 3 of them are going to be the same color. Okay, now check this out. If this edge is red, then we have a monochrome triangle. If this edge is red, well, then we have a monochrome triangle. If this edge is red, then we have a monochrome triangle. Now, let's suppose that none of those things happen. Then they all have to be blue, right? If any of those events happen, we're done. But if they don't happen, then we're going to get that these are blue. And that has to be, that's going to form a monochromatic triangle now. Is that not a lovely proof? Right? Right? Very, very satisfying proof. Yeah, this is the kind of thing that like just sticks with you forever. Super duper lovely proof, I think. But it's tricky, right? It's a tricky thing to come up with. So we know that this number has to be bigger than 5, right? There's a coloring of the 5 vertex complete graph with no triangles. And we know that it has to be equal to 6 because any coloring of this complete graph, right? Any coloring we pick whatsoever will have this structure. It'll have to have a monochrome thing. Okay, so now we're going to get into mixing this graph theory and the probabilistic method. Our first example of the probabilistic method was that, you know, in any 100 coin tosses, there's a run of, or no, there are coin tosses without a run of 99 coins. We're going to do something similar to show that these numbers must grow exponentially in K. So what we're going to do is we're going to argue that there must be exponential growth of these Ramsey numbers. It's hard to see for the small example, you know, 336, but asymptotically they grow very fast. And this paper by Erdős, this 1943 paper, sort of started. Right. Yes. River, Kevin, super duper great question. Why? Like what? Shouldn't this just be RK or something? Right? Yeah. So in the literature, yeah, it generalizes to M and K. So R and K is either a red CN or blue CK. Yeah, so every coloring of this graph has either a red CN or a blue CK, but here they're playing sort of symmetric roles. Yeah, super duper legit question because that notation looks really weird. We're only going to deal with the so-called diagonal ones, right? Where the 2 parameters are equal. Okay, so we're going to show that these grow exponentially in K. And here's the crazy idea, okay? We are going to make a coloring randomly because our constructive techniques are like not powerful enough. So we're just going to consider a random coloring. Like we're just going to toss a coin for each of the edges. So we've got n vertices. and each pair of vertices defines an edge for us. And we're just going to toss a 50-50 red-blue coin for each edge. So what we're going to do is we're going to pick out a subset of vertices, and we're going to say, what's the probability that that subset is monochromatic, right? For any collection of k vertices. Here, I should probably draw. Right, we're just going to grab a collection of vertices and say, like, what's the likelihood that the graph in here, or the coloring in here, is monochromatic? So this defines a complete subgraph. And now we're doing this linearity of expectation move. We're saying that this will be equal to 1 if this thing is monochrome. It'll be 0 otherwise. So our expectation is the probability that this thing is monochrome. So this is our monochrome blue term. And this is our monochrome red term. Notice the exponents here. These are edges in SK, right? So there's K, choose too many edges. And we want them all to be the same color. If we do a little bit of rewriting, it looks like this. Cool. Okay. Now, how many monochrome collections can this thing have? Well, we're going to add up over all possible subsets, just like we did with the coin tossing example. We're going to split this random variable into a sum of simpler random variables. So we're saying the expectation of the total number is the sum of the expectations of these collections. Right, so this is saying how many subsets? And then we're just multiplying the probability that each one's monochrome. Okay, so what do we got here? We have n vertices, and we're looking at subsets of size k. So how many subsets of size k are there? Yeah. Kevin, this choose notation, right? So Kevin saying or n choose k, and I tend to write that in this notation. Right, this is a binomial coefficient notation. Yeah, perfect. So we've got a bound for the probability of being monochrome. We know how many subsets there are. So the expectation is just the number of subsets times the probability that each subset is monochrome. So here's like what happens when we apply this key insight. If this expectation is less than 1, then there is some coloring without any monochrome CKs. And this is like a nice, fairly straightforward formula, right? I could plug in values of this formula and get a sense for what's going on. I could ask Wolfram Alpha or something like, how likely is it that, if I have a graph with 1,000 vertices, how likely is it that it has no monochrome 100 or something, right? We can plug in values. And that's a huge amount of progress. We don't actually have to write down like these graphs and these colorings. We have a formula that we can control and see what's going on. Cool. So we're going to make some estimates to simplify this formula even further. How we get these estimates, not super duper important. Let's just say that they're really big estimates. So we're going to control n choose k by n to the k over k factorial, and k choose 2 by a half k squared. If you want, I can come back and talk about these later if you want like those kind of like problem solving hacks. But let's see what happens when we make the following assumption about the relative size of k and n. So when we assume that n is growing exponentially, we get the following really nice sequence of inequalities. So we have our formula for the expected number of monochrome subgraphs. Right? We can apply this formula to get rid of the binomial coefficient upstairs. Then we can apply this formula to get rid of the other binomial coefficient. And now we can plug in our size bound. Right, so n becomes this formula. Now check this out. This was chosen so that we get a k to the power k. That's going to turn into a k squared. And that's going to cancel out this k squared. So when all the dust settles, this cancels out to 2 over k factorial. And that's just awesome, right? That's like as nice as a formula can get. And when k is bigger than or equal to 3, this is less than 1. So if n is 2 to the k over 2, if we're at the size 2 to the k, then we expect no monochrome triangles at all. Okay. Questions here, thoughts here about these estimates so far? Right. So this value of n was chosen to make this argument work out. If you take values of n bigger than this, right? Like if you take like 1 billion times this n, the argument will still work out, but you'll have factors left over. So this actually works for all n bigger than 2 to the k over 2. Because, and that establishes the lower bound for us. Once we know that these graphs have some coloring with no monochrome stuff, that establishes the lower bound we want. Yeah, it's kind of like a weirdly quantified statement, but yeah, we set n equals this value. It makes all the algebra work out nicely, and any bigger n would still work. Okay, cool. So what's this saying? This is saying if we pick n to be growing exponentially in k, then the Ramsey numbers must grow faster than an exponential lower bound, right? So this is exponential. Okay, so the Ramsey numbers grow quite quickly. And the kind of the algorithms side of things is that, let's say you're designing a computer network or something that you want to be like fault tolerant. You don't want any collection of things to interact too much and break it or something. One way to do that would be to just randomly color these edges, and you probably wouldn't have any of these clusters. And it'd be very, very fast to generate such a coloring. It'd be as fast as just tossing a coin for each of the edges. Cool. I want to give you, like, flipping this argument on its head. I want to give you a sort of a different perspective on this, one that doesn't involve probability, but has the same kind of conclusion. So let's do the same argument via counting this time. How many colorings of this graph are there? Right, let's just count all possible colorings. Well, it has n choose 2 edges, so we get 2 to the n choose 2 colorings, right? Lots and lots and lots of colorings. How many colorings have a monochromatic CK? Well, any subset of vertices can be colored red or blue. And then everything else will just whatever. So we're going to get, this is our term for red and blue, that 2 there. And then this is our term for choosing the vertices. We color these monochrome. And then everything else gets colored arbitrarily. Okay, so there are at most this many colorings that just have a monochrome subthing. So there will be colorings without monochrome CKs when the total number is bigger than the number of ones with monochrome. And if we divide out, we get this. So notice that this is the exact same formula we had for the expected number. So this probabilistic thing, this expected value thing, can be unraveled and can be talked about in terms of just counting. Okay, this is the same argument in terms of counting. But I think that the probabilistic method allows you to use tools from probability theory, things like Markov's inequality or Boole's inequality, that you wouldn't be able to get at just via counting. I think it provides a nice language and a set of tools for working on these combinatorics problems. So this is the same argument done just via counting with no probability language. So the references for this, the early paper, some remarks on the theory of graphs, is where Erder started using these tools. There's an amazing book that I would absolutely love to do a reading course on with an interested student, The Probabilistic Method. And what we've done today is example 1 of this book. Okay, there's a really beautiful theory using those probabilistic tools. And we've covered just the intro to it. So I hope that was as satisfying for you as it was for me to give this talk. I'm really glad to be here sharing this with you today. Oh, there's a random quote. Ooh. Before I get into the random quotes, I am here to answer questions and I'll happily chit chat. There's one announcement I want to make is that Ben is actually going to give our next talk. So if we look here, our next talk is same Zoom link, same time. Ben Chislet's going to tell us about ray tracing, which is a very cool algorithmic way of drawing realistic photos on computers. So I really look forward to that. What's Ben's quote? Erdős asks us to imagine an alien force vastly more powerful than us landing on Earth and demanding the value of R55 or they will destroy our planet. In that case, we should marshal all the computers and mathematicians and attempt to find the value. But suppose instead they ask for R66. In that case, he believes we should attempt to destroy the aliens. So nailing down the exact values of these diagonal Ramsey numbers is hard. We've shown a probabilistic method that shows their growth rates, but actually knowing the value of R55 is an open question. And I think it's the lower bound now is people think it might be 49 or 50. And then R66, no one has any idea. So super duper cool, super duper exciting stuff. Are there questions people would like to chat about? Oh, Ben's got the more accurate numbers. It's 43 to 48. I misremembered. Can I circle back to those estimates? Yeah, sure. Yeah, definitely. Yeah, so I just threw these down. We didn't really talk about them too much. Is there anyone curious about them? Would people like to hear where those come from? Okay, River. Well, thanks for coming out today. I'm glad that you enjoyed the talk, and we hope to see you at another seminar. Okay, so let's check out this estimate. So the formula that we usually write for this is n minus k factorial, k factorial. Right, so we can see that there's some parts that are common, right? We've got this k factorial in the bottom, k factorial in the bottom. So what we're going to see is that this is going to be like 1, 2, n. Oh, geez. I have got myself into a mess now. Okay. K factorial. Okay, so what we can do is we can cancel off lots of these terms, right? All of these guys are going to cancel off. Right, and what we're going to be, so all of those go away and we get a couple terms remaining like this. And what we're going to do is we're going to replace all of those terms on the top with n's. Right, the biggest they could possibly be, the biggest the uncanceled stuff could be is n's. Right, so we destroy these terms. We're left with k remaining. right? There's going to be k things, and we just make them as big as possible. Yeah, it's a really, really nice argument. Here, I think I can fit the other one in this box. Right, yeah. Is this probabilistic method useful when we start talking about infinite graphs? I'm not an expert. I think it's mostly useful for finite stuff. Infinite stuff, I don't think the methods carry over to infinite graphs very well, but I would love to be corrected. I actually don't know. I guess that's why we should check out that book. Oh, hey. Yeah, Jesse, didn't you want to talk about compactness? Right? Are you the seminar speaker who wants to talk about? Yeah, mathematical logic. So this Ramsey stuff, showing that the Ramsey numbers exist, can be done using compactness. So that might be an interesting thing to include. Oh, you know the proof. Oh, excellent. Okay. I've surprised. Okay, cool. Nobody. Excellent. Are there other things people would like to chat about? How did the foundational principle or lemma come about? Yeah, that's great. I would like to know about that as well. I think like, I mean, people before Erdős noted it. So probably my guess is something like this. My guess is that people were doing this kind of stuff via counting and noticing this gap here. Right? They were probably noticing that there's more stuff here. And I think that Erdős realized that you could translate that into probability terms. So I think this is like quite old. And then this is kind of new Erdős stuff. So probably by seeing a lot of these kinds of kind of the left-hand side argument, this kind of counting arguments, and then realizing, oh, I keep doing the same thing, I could rephrase that in a probabilistic language. That's my guess. Yeah. Excellent. Yeah. Thank you very much for coming out, folks. It's been a pleasure. If you have something that you'd like to talk about, please contact Lisa or I. We'd be happy to have more speakers. This is a blast. This is really fun, and I'm glad that you're coming out. So we will see you next week. After the talk's over, I'm going to